Okay, so sorry, that was the typo, so it's supposed to be emergent non-locality.
Oh, okay.
From alternative action principles. And this is based on work that I've done with Tommy and David. And this is a paper reference there. And this talk kind of has an interesting genesis, actually, because I finished this talk and prepared it on the train here. And then when I came yesterday morning, Tommy just told me, before you give your talk, you kind of have to talk to Alexei. And so I talked to Alexei, and it turned out that some of the points in this paper that we're going to talk about were not completely correct, but I'll get to that when we come to that. But I just want to make sure that you all know that Alexei deserves a lot of credit for this not being horrible. Okay. So it's really nice to be, so let's see. So it's...
You shouldn't just move the mouse.
Okay, so it's really nice to be straight after Miguel, because now he's introduced these general type of scalar tensor theories to you. And I'm going to talk about one particular type which has some interesting phenomenology. Well, not phenomenology, but it has an interesting structure. So it's a very constrained type of these scalar tensor type of theory, which is called C theory. So the outline is that I'm first going to present this C theory and something about the sort of non-local gravity that we think is sort of vaguely related to, at least. And then I'm going to, originally this was going to be a proof of equivalence, which doesn't exactly hold. It's going to be a proof of non-equivalence. And then I'll give you an outlook after that. So the motivation, the starting point for this is that there are alternative variational principles. So let's say you have an f of r action like this, and you can ask yourself, how do you variate this? Of course, you can do sort of the usual thing and just do the metric variation, where G mu is your usual metric, mathematic. But when you have just normal GR, not f of r, you get the exact same equations when performing the variations instead with respect to your connections. So you promote your connections from just being Christoffel symbols or geometric to being free functions, and you variate with respect to them instead of volumetric. And Palatini proved that this would be equivalent. So what if you do this for f of r? Like I said, GR, it's equivalent, but in f of r, this is not equivalent at all. You get a different, you still have this mathematic G mu, which is this one, but then in addition you have this curvature metric for which these connections now belong to. So C theories then, a theory that was proposed by Amendola, Karjanquist and Tommy, in order to make a framework in which you have a transition between these types of variational principles. So what you define is that you have your mathematic, your usual G mu, and then you define a hatted metric, which is related to G mu in this way. So it's exactly like the types that Miguel talked about, only that this C now is a function of this twiddly r, which I'm now going to tell you what it is. And this twiddly r is this hatted R mu is the Ricci tensor belonging to this hatted metric, and it's been contracted with the matter metric, just because it's the matter metric is what we use to contract indices in this framework. So in this sense, you see it's sort of a circular definition, because this one is sort of defined in terms of this one, which is defined in terms of this one, and so on. And then you define your action to be like f of r but with R being this twiddly R, and then it's just the usual pattern.
Sorry, can you remind me, is the Palatini f of R is still a scalar tensor theory?
Yeah, and this is still.
Is it just a different value of the potential you get, or a different Browns-Sticky parameter?
You get -3 halves Browns-Sticky parameter, which is special because it sort of cancels out the kinetic term in the Einstein.
Yeah.
Thank you.
Yeah. So the metric case, you of course get with this c equal to 1 or constant. Of course, I'm just going to assume that any normalization that you wanted is can just be absorbed into your F. And then you get the Palatini variational principle if you define C to be the derivative F this way. And then you can make a transition between these in any way you want. For instance, you can make a particularly simple one by having a linear transition like this, but there could be lots of others. You can pick your favorite transition then. And in this case, alpha runs from 0 to 1. So in 0 you have metric and in 1 you have Palatini. But of course this C theory framework has lots more theories than just metric and Palatini and what's in between. So I want to tell you a bit about the generic properties of these kinds of theories. So in a certain sense they are bimetric because you have both this matter metric and this atom metric. And like I said, it's a scalar tensor theory, and it's easy to see directly if you employ a couple of Lagrange multipliers to get these scalar directly, and then you get the theory which is defined in terms of two scalars, but only one of them is actually freely evolving. The other is given by the constraint equation. You can also define what R is in terms of, what really R is in terms of the matter R, and some derivatives of C in this way. But of course, we know that C depends on twiddly R. So what you can do then is you can say, okay, I have this relation for twiddly R, so I'm going to plug that relation in for all the R's in the C's, and then I get a much longer, much uglier relation between twiddly R, and some more derivatives of C, and I can keep doing this, and I get this eternal pattern of substitution and resubstitution. Which means that I also get this eternal expansion in R and derivatives of R for this term. So since there's this eternal structure of more and more derivatives and more higher order terms, it's natural to think that this is sort of has a non-local flair to it. So we were interested in trying to see what type of non-local theories this might be, at least vaguely related to sometimes. So we looked at a particular type of non-local theory, which is, I'm just going to dub conformal non-local theory, non-local gravity, which was proposed by Biswas, Sandstad and Siegel. And it's this function here, so this is a normal GR term, and then there's this additional term where F is an analytic function, but which has no truncation at finite n in the series. And this can lead to bouncing cosmologies, but these theories also have really nice quantum properties, so they can be renormalizable, and also you can even have ghost freedom in certain particular formulations or choices for F. So we would want to see if we can find a type of C theory that's equivalent to this. So the equivalence would then be found if we found some F of R which was equal to this. And so we look again at this R in terms of twiddly R in terms of the matter R, and C in its derivatives. And we can rewrite it this way. where now this h of CD is now the dimension of the space, is given in this way. And just from the structure here, we see that this h function is probably problematic in terms of going to these non-local theories, because if this one is non-zero, even if you perform some kind of partial integration, you will still have some terms that are not are with box, but these BRs. You still have terms like that. So you need to have this h term go to 0, and then there's a difference between different kinds of dimensions. Of course, dimension 1 is completely trivial. There's no actual theories present in dimension 1. So in dimension 2, this constraint gives you an exponential factor for the c, and then you can find this function of r is on this form. And this is really nice, but this is of course also because dimension 2 is quite trivial in the sense here. So when d is not equal to 2, this condition means that we have this functional form for c, and then we get this kind of term. We also get more higher order terms because of this term here, and this was exactly what Alexei pointed out, and which I guess he'll be elaborating on in the upcoming paper with Tommy. But it's still sort of nice to see that we have this sort of, even though we have these extra higher order corrections, we still see that there's at least a non-local flair to this, which is vaguely related to this, at least in dimension 2. C theory is a framework which encompasses Palatinian metric terms, and this has a sort of base non-locality inbuilt into it. And this might hint that there might be a general non-locality in alternative action principles, and this non-locality or this circular structure might also explain some of the lack of productivity of Palatini FFR. And some other things to do is like, so we looked at this C theory. You can also define this formal version of this, like Miguel just talked about from Bekenstein, and which he has also been working on. And we think that the sort of vague connection that we saw between this one and this conformal non-local gravity might lead to a vague connection between this and Leonardo's supernormalizable non-local gravities, which I think also Alexei would be looking further into. So, yeah.